This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Everybody, my name is Nicos Makris. I am the Addy Family Centennial Professor of Civil Engineering at Southern Methodist University. I work in structural engineering and structural mechanics. And it's a pleasure to be with you.
Yeah, thanks for being here, Nikos. Glad to hear about your work, and I'm really excited to hear about your study. But for folks who aren't initiated with dampers and how engineers use those as protective devices, can you tell us a little bit about that and what sort of hazards are dampers even useful for?
Very good. So in modern earthquake engineering, we have advanced this concept of enhancing the response of structures by adding specially designed devices within the skeleton of the structure or at the foundation of the structure that they will either absorb the earthquake energy rather than this earthquake energy to damage the structure, or to isolate the structure so that the earthquake energy does not penetrate into the structure or does not penetrate to a great extent. So the first idea is seismic isolation, where we isolate the structure and the structure, the motion of the structure somehow decouples from the foundation. But there are situations where we have to fight the earthquake once it has entered the structure, and then we have to enhance the structure with energy dissipation devices. And these, we call them, for simplicity, dampers, because they damp the seismic induced energy. And by damping this energy, we manage to reduce the interstory drifts between the stories of the structures, which is what creates damage in the skeleton of the structure.
Okay, so at the end of the day, it's really, I like how you put it in like the skeletal structure. We're recording this on Halloween, so it's very very apt.
Yeah.
So the dampers act kind of like almost like ligaments or tendons in the body, making sure that the energy that's transmitted from things like earthquakes are distributed or absorbed rather than doing damage.
Exactly. So
drift.
So perhaps the easiest analogy that everybody has a daily experience are the shock absorbers in the car.
Yeah.
So the car, as it rides over a bumpy road, it has a tendency to vibrate, but to have the shock absorbers to reduce its vibrations, right? So the same way the dampers that you use are very similar energy dissipation device to suppress the vibration of buildings when they're being excited by earthquake shaking or wind vibrations, or sometimes even traffic vibrations in bridges.
Yeah, and a lot of times those shock absorbers in your car have oil and air in them, or some other gas, nitrogen or something like that.
Exactly.
Your particular project and research, you're working on a pressurized sand damper. That sounds really interesting. How did that work?
Exactly. So this is the main innovation of what you have done. So actually, you hit the nail on the head. The majority of dampers of these energy dissipation devices that we use for seismic protection until now contain oil. So this is silicon oil that is very similar to the silicon oil that are in the shock absorbers of the cars. Okay. Now, the challenge with these devices when installing structures is that structures are subjected to a variety of loads. So we mentioned earthquakes, we mentioned wind-induced vibration, we mentioned traffic-induced vibration. So, and these are excitations that have different characteristics. So for instance, an earthquake induces very violent vibrations, but for a short amount of time. whereas a windstorm may induce less violent vibration, but for prolonged periods. And traffic loading may induce smaller amplitude vibration, but these are perpetual vibrations as traffic goes through the bridge day and night, right? So we have to design these devices to, at the same time, withstand long stroke, violent vibration from earthquakes, but also to be able to be resistant to these prolonged vibrations that may fatigue the device, right? And in the past, we had more than one situations where dampers that were installed for seismic protection of bridges, mainly in California, right? They failed not because the dampers saw an earthquake, but because the dampers were moved for prolonged periods of time, mainly from traffic loading, right?
Oh, wow.
So, and this perpetual motion ended wearing out the end seals of the dampers, right? And then the damper starts leaking, and when the damper leak, then it has no more use, right? It is useless.
Right. It's just like your shock absorber on your car, or a constant velocity joint leaks the grease leaks out and it locks up.
Exactly.
Doesn't do what it's supposed to do anymore.
So this idea of addressing the problem of failing of the end seals that leads to leaking was something that was in my mind after I have witnessed these failures in the late 90s and early 2000s in California, in association that oil, when its temperature changes, it either goes from hot to warm or warm to hot, its viscosity, so its ability to dissipate energy changes also, right?
Yeah.
So an oil damper will behave differently if it is in, let's say, minus 10 degrees Fahrenheit, or if it is at 110 degrees Fahrenheit, right? So it will behave differently if you place it in the Mojave Desert or if you place it in Alaska, right? So we had also in our minds the idea perhaps we could develop a damper that its behavior is not so much temperature dependent, right? So these two challenges, in association with the need to have a device that can undergo long strokes. So when you have a damper installed in a building, it will go displacements of the order of inches, like 1 or 2 inches, right? So according to how much one story is moving to the other, or maybe a little more. But when we install dampers in bridges, the displacements are much bigger, right? There are several inches. There can be, so the design displacements can be 20 inches, right? Or even higher than this. So 20 inches, for those who are more familiar with the metric system, 20 inches is half a meter, 40 inches is 1 meter, right? So we have seen displacements in decks because of strong ground shaking, mainly because of these near source ground motions that exceed half a meter, exceeds 20 inches. So we had all these challenges to address. So long strokes, no leakage, and temperature independence. So the material that can satisfy all these requirements is to replace the oil inside the damper with something that can flow, but it's not a fluid. So we replace this with sand. And in order for the sand to work, we came up with an arrangement that you can pressurize this sand at some nominal pressure. So it can be 1 megapascal or 2 megapascal or 4 megapascal, depending on how much we want to be the force output from the damper. So this design gave us the possibility to have some liberty in designing for a given force output that is desired.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.